Thank you everyone for joining our webinar, Increasing Business Agility with Real-Time Processing using Apache Hadoop and Spark powered by Nebula and Scalr. My name is Nguyen with Nebula's Product Marketing. I also have with me on the line Thomas Orozco, Product Manager from Scalr. For today's session, we are going to walk through what's driving the need for real-time processing, identify use cases and design guidelines for building an elastic real-time compute infrastructure that can support Apache Hadoop and Spark's real-time processing, and close out the webinar with a great demo. I think we can all admit that big data is one of the most used buzzwords, but reality is that every business in some form or fashion rely on big data's 3 V's to maintain a competitive edge, those being volume, variety, and velocity of data. The volume of data will continue to grow, especially as more users and devices connect to the internet. As a result, the variety of data will also continue to be more diverse. And in turn, the velocity of data received is going to be faster and faster, no thanks to higher speed networks that need to be in place to support the numerous connected devices. And which, by the way, will in turn create more volume, which then impacts the variety of data again. And as you can see, it's a never-ending cycle. Businesses depend on data, but historical data is no longer sufficient to maintain a competitive edge. Back then, gaining insight into data within days was considered outstanding. Now the expectation is within minutes, which can make a difference between a brilliantly handled crisis and a fully blown social media disaster. Data after the fact is losing competitive edge, and businesses want the ability to act right now as events happen. Therefore, businesses are looking to leverage real-time streaming analytics for continuously collecting and analyzing data and to course correct to positively impact the outcome as events unfold. Real-time analytics, however, requires a real-time processing tier. The best way to capture the value of incoming data is to analyze and take action on that data the instant it arrives. If you're processing incoming data in batches or scheduled jobs, you've already lost time and have incurred latency. The value of that data disintegrates as more time is passed. So in a batch processing model, data is first stored, then it's indexed, and then processed by queries later on. As a result, businesses are acting on what we would call data at rest. In contrast, real-time stream processing takes the data while it's in motion or as it traverses the system server. However, real-time streaming data is like a fire hose. It requires a lot of compute and memory power to analyze data as it's received. But that's not the main problem. You may have the power of compute in place today to support this, but as the speed of data continues to grow at high velocity, the ability to dynamically scale more compute and memory to process the increased data feeds is lost. So in essence, you lose the value of real-time streaming. But an on-premise cloud compute infrastructure orchestrated with an intelligent cloud management platform helps overcome this roadblock. The combined solution from Nebula and Scalr can deliver an elastic compute infrastructure that can react and dynamically allocate the compute power on demand as the incoming data feed rates increases. So instead of simply storing data to be analyzed later, I think we've reached the point where it can be analyzed as it's consumed at high velocity because the underlying infrastructure from Nebula and Scalr can adapt in real time as well. Data feeds can potentially come from a variety of sources depending on the use case and business requirement. Some examples of user, machine, and sensor-generated data may come from smartphones, wearables with GPS sensors, physical sensors in buildings such as energy monitoring devices, internet-enabled transportation, and more commonly, click streams, social media streams, enterprise applications, SaaS applications, and so on. Clickstream analysis is one of the common use cases where businesses can personalize pages or adware content to the user's clickstream. To be successful in personalization, however, you need to react fast to what the user is doing and the events happening in the outside world. Sentiment analysis and data mining of user, machine, or sensor-generated content can also build a better custom engagement. For algorithmic trading, it's not just about nanosecond packet latency, but it's being able to feed real-time data into the systems that trend and compare against historical data, which then can better predict outcomes based on events that are occurring now in near real time. Perhaps the most common use case for real-time processing of data is for optimizing IT management. These may include log processing, analysis, and log-driven alerts. So for example, infrastructure fault protection. Stream processing can be used to learn about network conditions and deliver better QoS for video applications to avoid the dreaded screen buffering in real time. For fraud protection or security threat protection, historical data can be fed to real-time systems to find if there are any deviation in real-time streaming data. If the deviation is beyond a certain threshold, for example, it can be tagged as an anomaly. So these are just some sample use cases, and businesses today are realizing the benefits of analyzing data streams in real time. I'm now going to pass this over to Thomas, who will provide a technical overview and design guidelines for a real-time processing tier.
Thanks, Wei. So the first question, of course, when we talk about Hadoop stream processing is really why use Hadoop for this purpose. There are, of course, plenty of alternatives that exist. One of them would be to use Apache Mesos, which actually also lets you run Spark on it. You could also use Storm or just like a traditional message queue such as Kafka or RabbitMQ and use your own processing tier, which may be built using any technology you like. So first off, let's actually look at what the actual benefits of using Hadoop and Spark for this purpose are. So there are mainly three unique benefits, as you can see. They're really threefold. The first one is really that both Hadoop and Spark offer a really high-level API. So they have lots of abstractions that will help your engineers basically be more efficient with them. Here the comparison is really with a message queue and a custom processing tier. If you're using Hadoop and Spark, you have the Hadoop Distributed File System, HDFS, as a storage abstraction, which basically means that wherever your application is running in your Hadoop cluster, it actually sees the same file system and all your data is redundant. It doesn't get lost if one server dies and so on and so forth. So it really simplifies file system interactions from your engineer's perspective. Likewise, Yarn, which we'll talk a bit more about it, which is the Hadoop scheduler, which is used to actually run Spark jobs. Yarn itself will take care of handling node failures, handling infrastructure failures, even job failures. If one of your job fails, it can be rescheduled somewhere else. So the first benefit is really that high-level API, which really makes it simpler to design and really focus on your data processing instead of focusing on your infrastructure that's going to be underneath. And that kind of leads us into the second benefit, which is a very strong separation of concerns. If you're using Hadoop and Spark for your real-time really two different concerns. Your data team works on creating basically Spark jobs that process real-time data and actually store that data in HDFS on the Hadoop file system. Whereas your infrastructure engineering team is then going to be in charge of actually keeping that Hadoop Yarn cluster alive. So it really simplifies concerns. Each one of them has a very specific job, and that makes it easier to find engineers to work on those problems and, generally speaking, to be more efficient in your organization. And finally, the third benefit is, of course, that using Hadoop and Spark really integrates pretty well with traditional batch jobs. So just like we mentioned, batch jobs are really becoming probably less and less relevant, but there are still some use cases where they may still be relevant in cases where you don't actually need real-time data. He was giving that example when you want to analyze historical data to be able to know whether the real-time data is a deviation from that pattern. So that's why using Hadoop and Spark becomes very relevant, because what you can do is process your data, process incoming data in real time using Spark, and then actually feed that data, maybe pre-processed data, to your HDFS file system, where you can then run MapReduce tasks on, so batch jobs on. So the idea is that if you're already running some batch jobs, using Hadoop and Spark for real-time processing will integrate very well with it. So these are really the three main benefits and the three main reasons of using Hadoop and Spark for real-time processing. So now that we know the high-level architecture, like the high-level benefits, let's look at the actual infrastructure that would support it. So architecturally speaking, we have three main tiers in our infrastructure and in our setup. At the very bottom, you have the HDFS file system. So HDFS has been, so that means Hadoop file system, has been a part of Hadoop. It's an historical part of Hadoop that's been there since the beginning. And it's basically a distributed and fault-tolerant file system, which means you spread it out across multiple nodes, and it takes care of replicating your data and handling node failures. Note that originally, Hadoop also bundled something else that was called MapReduce. So not the algorithm, of course, an actual implementation of MapReduce, which is why Hadoop has the reputation of only being useful for batch jobs. But this has actually changed with Hadoop 2, when MapReduce was replaced with something that's called Yarn. So Yarn means yet another resource negotiator, and that's really what it is. It is a task scheduler. So it's basically, it exposes an API, and you can submit tasks to it, and Yarn will take care of scheduling those tasks on your Hadoop cluster. And of course, those tasks may be batch jobs. They may actually be MapReduce tasks, but they could also be real-time tasks using Spark, for example. And that's our last tier, Spark specifically. So Spark is an even higher level cluster computing platform, and really the benefit of Spark is that it has that Spark streaming module that's really focused on processing, on doing stream processing, and backing up its data to HDFS in real time, so that even if your stream processing crashes at some point, if your compute nodes go down, all the data is still on HDFS, and you can resume on some other node in real time. That's really the main benefit of Spark streaming. And of course, like I mentioned, Spark can be scheduled to run in Yarn on top of HDFS. So that's really the high-level architecture of those three tiers. Let's now drill a bit into it and see what this actually really specifically. Oh, well, first off, actually, I was going to miss a slide. First off, we actually have to consider the kind of the design principles. So the main thing about doing stream processing is that it's like scaling-wise, like Hui was explaining, scaling-wise, doing stream processing is very different from doing batch processing. When you deploy a typical Hadoop cluster, what you usually do is that all of your nodes are both acting as a data node, so a Hadoop HDFS node, and a Yarn compute node. Now, the problem with this is that scaling becomes very difficult, because it means that you have to autoscale. If you want to autoscale up and down, then if you tie the two tiers, you have to autoscale both your compute tier and your storage tier in parallel. And that's not something HDFS tolerates very well. Quite the opposite, actually. If you do autoscaling on HDFS nodes, you're very quickly going to find yourself in a situation where data has to be relocated whenever you launch a new instance, which is very inefficient. And when you downscale, you may actually get in a situation where all the replicas for one piece of data get deleted, in which case you actually lose data. So we'll actually look into this a bit more afterwards during the demo, so I'm not going to spend much more time on this, but the idea is obviously that decoupling the tiers enables autoscaling. So now we have those two design principles, the three tiers that we want, and the autoscaling requirement. The actual architecture is going to look like this. So first off, on the left, we have the Yarn cluster, so that's the compute tier. The Yarn cluster in Hadoop is really composed of three different components. One of them is the resource manager. So the resource manager is really the one where you submit your tasks, and it takes care of scheduling them on some actual compute nodes. So that's the Yarn master, if you want. One thing to be aware of is that the Yarn master does support HA, provided you have a recent version of Hadoop, in which case you'll want to deploy two of them. The history server is just there to remember basically the jobs that were completed earlier. It's actually an optional part, but you usually want to have it to be able to have some knowledge of what's running on your cluster. And finally, node managers. So node managers are a bit of a misnomer. The node manager is actually the Yarn application that's running on a given node. So these are the yarn slaves. So on each yarn slave, which is a virtual machine or an actual server, on each one of those yarn slaves, you have a node manager that is able to schedule jobs to run on that slave. And of course, the node managers are the compute tier, and they are what you'll. Now, the second tier of the infrastructure is the Hadoop storage tier. So that's your HDFS cluster. This has one name node. So the name node follows the same pattern as the resource manager. It's the master. It decides where data gets scheduled. And multiple data nodes. So these are the ones where the data is actually stored, and they are the ones you don't want to autoscale. Now, in addition to that, you'll usually want to add some client nodes so that end users can actually connect to the Hadoop cluster without SSHing into one of the actual Hadoop VMs. All of that can be managed using a cloud management platform from Scalr. The idea is that Scalr will take care of the provisioning and orchestration of all your Hadoop cluster. And of course, all of that will happen on actual private cloud infrastructure, which is provided by Nebula, which provides you with elastic and on-demand cloud computing.
Thank you, Thomas. Nebula helps enterprises achieve the fastest path to OpenStack. We deliver an enterprise-class private cloud based on OpenStack where our turnkey software is delivered using an appliance, which you see here on the top left, with off-the-shelf industry-standard servers for low cost. This turnkey solution provides seamless integration with existing enterprise resources, such as Microsoft Active Directory for identity, NetApp for storage, and we've introduced an enterprise VLAN model, by the way, code which we've contributed back to the OpenStack community that enables our private cloud to seamlessly integrate with existing customer VLAN networks. It's open and secure, where our appliance model approach allows for separate security domains with protected TLS private keys, with a trusted platform module and boot attestation, where we will periodically check to make sure that the images on the servers are not tampered. And we also provide SE Linux for protected instances. With an appliance model, every cloud is identical, which allows for simple software upgrades and a turnkey ecosystem platform. At the end of the day, we deliver a curated OpenStack solution so that customers spend time using the cloud versus building the cloud. Our mission is to create a turnkey enterprise IT solution that scales at all levels. So you can start with 5 servers with no overhead. In other words, all 5 servers can be used for compute and storage resources. We can scale to a full rack or to multiple racks. You can connect off-the-shelf servers from Cisco, Dell, HP, IBM, and Supermicro, for example, to the Nebula Cloud Controller. There's no manual imaging or system software configuration on the servers. No editing of the OpenStack config files, ever. Once connected to our cloud controller, we take control of those servers and transform them into cloud nodes and pool the compute, storage, and network resources, making them available to multiple projects for self-service provisioning. As mentioned earlier, we are the only enterprise-ready cloud that provides turnkey integration with existing enterprise identity, storage, and networking VLANs, supporting cloud workloads with open APIs for a turnkey ecosystem, in this case with Scalr, for the auto-scaling. Configuration is done through a simplified GUI, which provides a self-service model for quickly deploying the resources for the projects. So as Thomas mentioned earlier, the processing tier, in this case the application and the infrastructure, must be able to auto-scale compute resources as the volume, velocity of the data feeds increases. So in this case here, with the Nebula Cloud Controller, on the top of rack for that matter, you connect the industry standard servers to our controller. We then pool all the compute, memory, and storage resources into a common shared resource pool, which then it provides a scale-out readiness. And so then as the Real-time data feeds continues to increase, right? The yarn tier can be provisioned to scale out across multiple servers with Nebula and Scalr. And then more importantly, though, I think it's not just about scaling out, but then once the data feeds or the bandwidth decreases, that the resources can be deprovisioned back to the share pool where it can be allocated to other projects. So it's about efficiency and better use of the actual infrastructure itself. I'm going to pass it back now over to Thomas for a very brief introduction of Scalr, and then we're going to jump into the actual demo of the Hadoop Spark and how Nebula and Scalr powers that autoscaling.
So thanks, Rui. So before we show that demo, let me actually set the context with a quick architectural overview of Scalr. So at a high level, Scalr is really middleware. So it sits between the end users of your cloud, so users like developers, IT users, finance users, and the actual cloud platforms that they may be using. So that's cloud APIs like Nebula's OpenStack standard APIs, something like AWS.
Scalr itself will not directly talk to any of the underlying hardware, which is what Hui was mentioning just earlier, that Nebula, you use the controller itself, and the controller then integrates and manages your industry standard servers. The idea is that Nebula takes care of pulling those servers into a pool of resources and then exposes those resources using the OpenStack standard API, which Scalr can then basically consume to provision and manage resources. Now, in addition to that, Scalr will also do some levels of server orchestration, and we'll actually look at that a bit afterwards during the demo, meaning that Scalr can actually manage your resources, execute scripts on them, configure them, and so on and so forth. But we don't touch any of the underlying hardware. We just talk to the API and the servers. Now, moving on to why Scalr is used in enterprises, there are three main reasons. The first one is really for resource orchestration. So that means provisioning resources across hybrid clouds, meaning maybe a Nebula private cloud, probably, maybe on the other hand, some public cloud resources, for example, on AWS. The idea is really when you provision those resources, Scalr enables you to do that in a templated manner, so that you can, for example, define what a Hadoop cluster looks like. Let's say someone is a systems engineer, they can prepare a Hadoop cluster that's ready to use.
And then someone like a developer may be able to reuse that to deploy their own Hadoop cluster using this template that was created by the systems engineering team who has more experience.
Beyond that, Scalr, once the resources are provisioned, Scalr also provides lifecycle management, such as auto-scaling, which we'll explore in more detail afterwards. Now, in addition to that resource orchestration, Scalr also provides a policy definition and enforcement. So here the idea is that when you adopt a cloud like Nebula or AWS, you basically put a great deal of control into the hands of your users. Meaning you provide them with self-service access, so that means that it's the usual saying that with great power comes great responsibility. You give them a lot of power, they have to kind of take responsibility for this. But typically, in an enterprise setup, you can't really afford to give all of your end users that kind of control. You can't have every developer make decisions as to what networks should be used, what instance type should be used for different types of deployments. Or maybe in some cases, when you have a large organization, you can't actually even trust them to do that. So what Scalr then provides is the ability for IT to regain a certain level of control over the usage of its resources. Through lease management, for example, which automatically decommissions resources after a certain period of time, network policies that define where resources can be deployed, or of course role-based access control, which is more of a feature-oriented control. And that's actually the example we were talking about a bit earlier with the client nodes. Using something like Scalr, you can make sure that only that data engineers can only provision client nodes, and that those client nodes are small instances, are launched in a restricted network, and that they get decommissioned when they're no longer used. Whereas the systems and the infrastructure engineering team will have more access to actually provision the Hadoop cluster. Now, finally, the last aspect is that Scalr really provides centralization, meaning that once you have deployed those resources and you started managing them, Scalr will also provide a single point of integration.
The idea here is that you can integrate your ITSM solution or your CMDB and do that with Scalr once.
And then take advantage of that integration across any cloud you may be using. So say you're currently maybe running a small POC on AWS maybe, then you want to use Scalr to manage it. Well, as soon as you get Nebula in-house, you can, all the integrations you did once, they automatically transfer to Nebula as well. Even if you're running multiple Nebula clusters, that's another way to share those integrations. In addition to that, Scalr will also provide cost reporting, which we'll explore in a bit more detail during the demo. So of course, Scalr is actually trusted by the enterprises that you can see listed here, and some of the content from this presentation is actually coming from our experience working on Hadoop deployments with customers at some of these organizations. So now, without further delay, I'm going to be jumping on to a demo of the solution to actually show you how you do that Nebula plus Scalr Hadoop deployment. So this is this was all logged in before, of course. So what you're seeing right now is this is the Scalr UI. As you can see, I have multiple environments set up, but one specifically is the Hadoop environment. Nebula is lit up here, so that's because Scalr was connected to Nebula. So I'll just click on this for a quick explanation. The way Scalr is connected to Nebula is through the standard OpenStack APIs that are exposed in Nebula. So you can see we're using Nova to connect for compute. We have Cinder for volumes. We also have security groups coming from Nova. So these are really the APIs exposed by Nebula that Scalr will be able to consume.
So now you can see that we have all of these supported clouds. You'll also note that we have two. We have Nebula and OpenStack. That's because Nebula is certified for Scalr.
That this basically guarantees better success. Inside of Scalr, we can actually have a look at our resources. So this is my Hadoop cluster. So of course, it's a small cluster. This is just a demo for a webinar after all. So you can see that we have 7 servers running right now. We have both of our YARN master and HDFS master running on the same node, and then you can see our HDFS and YARN clusters. Now, all of this is visible through Scalr, of course, but if we go on to the Nebula UI, which we can see right here, we can see the same resources in Nebula. So there you can see the resources I provisioned in Nebula. This is my Hadoop cluster, all my instances, their IPs, their instance types, and so on and so forth. I also have block storage provisioned in Nebula. So just like we was mentioning, Nebula integrates with a number of technology partners to provide block storage, which is basically on-demand block storage. Scalr and that is exposed through the Cinder API. So Scalr can consume that, and in this case, we provisioned those 3 volumes that you can see for our HDFS tier through Scalr. They were provisioned in Nebula. Okay, so let me then move back into the Scalr UI, and before we actually begin with the demo proper, let me just get a few architectural concerns out of the way. Right now I'm logged in as a user in Scalr, which is, you can see right here, that's myself, and I actually have full permissions on that environment. I'm actually the owner of that environment, so you won't see me join that demo limited by things like ACLs, or access control or access restrictions. Now, of course, it is possible to layer on such ACLs. So this is done in Scalr through that ACL menu that you can see right there. One thing to note is that it's also possible to integrate with LDAP or Active Directory to do this, to actually derive ACLs from LDAP or Active Directory. Meaning that if you do that, then based on someone's groups in LDAP or AD, they can directly just log into Scalr
and then get access to all the clouds that were added to your Scalr environment. So now that being said, let's move to the farms list in Scalr and see how our Hadoop cluster was actually configured to give you a concrete idea of how Scalr is used.
So in Scalr, a piece of infrastructure is represented as a farm. In my case, you can see I have this Hadoop cluster farm, which is locked since I didn't want to accidentally terminate it. Now, this Hadoop cluster farm is actually composed of, let's just wait for it to load. This Hadoop cluster farm is composed of multiple tiers, which you can see right here. So we have the Hadoop master tier, the Hadoop HDFS tier, and the Hadoop YARN tier, which, like we mentioned during the first part of the webinar, each of these tiers is configured individually and scaled individually. So the master tier is right here. Again, we have both masters on the same node. That's not what you want to do in production. That's just for a POC, of course. We only have one of those. And as you can see, we get access to all the features that are exposed in Nebula. So we can get a floating IP. We can choose any instance type that's available in Nebula. And we're also consuming the storage that is exposed by Nebula. So in this case, we have a storage setup. That's the 20 gigs volume that you were seeing a bit earlier in the Nebula UI that was provisioned through that tier. Now, each of these tiers is configured a bit differently, as you can see. So our Hadoop HDFS tier has no auto-scaling. It's a minimum of 2, maximum of 2 instances. No changes will ever be made. Do note that if one of these instances dies or crashes, of course, Scalr will replace it, meaning that it's really a declarative approach to infrastructure. So you don't just log into Scalr and launch a bunch of instances, and then if they die, forget about them. Instead, you define a state that you want to enforce, which in this case is, I want 2 Hadoop HDFS nodes running, and I want each of these nodes to have a 40 gigs volume mounted at MNT DFS. Well, in that case, if one of those nodes crashes, Scalr will automatically replace it and reattach the volume to the replacement. If the volume itself died, then Scalr will provision a replacement volume. Finally, our last tier is the yarn tier, which you can see right here.
So that tier is configured to use auto-scaling. As you can see, we scale between 4 and 8 instances, and this is configured to scale based on load averages.
We can actually see the history of load averages on this instance to help us make a decision about it. You can see that in my case, I'm pretty conservative. It's unlikely that my load will go over 5 very soon. So that's the provisioning part that I was describing earlier. Beyond provisioning, Scalr can also help you orchestrate and basically run some scripts and some automation on the resources that you provision in Nebula. So in this case, we have this automation that's set up that basically runs some scripts that automatically configure our Hadoop nodes for us. And Hadoop itself is actually deployed using Chef, which is exposed through Scalr, as you can see right here. So we have this cookbook that is used to deploy the Cloudera distribution of Hadoop, and we use this to deploy Hadoop itself. Note that, of course, if you're using Puppet or Salt, that it's also possible to use those. With Scalr. Chef is just, of course, just one option. So that's going to be that's basically the. I'll go back to the Scalr UI in a bit, but right now I'm going to move on to the UI which you're probably all waiting for, which is of course the Hadoop UI. So this is the Hadoop cluster. Note that Scalr actually set up DNS for me, so I can actually connect to it directly. So this is my Hadoop master. As you can see, I'm connected to the Yarn UI, and as you can observe, I have my 4 yarn nodes which are online right now. None of them are actually being used because I'm not running anything on this Hadoop cluster right now, although I can actually go into the history and see that I run a few tasks over the past few days. Then I also have, of course, my, let me actually close this.
I also have, of course, my Hadoop name node, as well as the 2 associated data nodes that you can see right here. So this is the master for the HDFS system. Now, of course, in a cloud environment,
sometimes your resources tend to crash. So that's actually what happened with our node right here. I actually crashed it intentionally for the purpose of the demo, but this one, as far as Hadoop's concerned, is dead. So when that happened, it was a pretty brutal halt. When that happened, Scalr actually noticed that this instance had been halted. It's one of those that you can actually see here. That's the one. Once this instance had been halted and disappeared from Nebula, Scalr noticed that and automatically spun up a replacement, which, as you can see, has the same hostname but a different IP. That was my replacement that was spun up and then orchestrated. The volume from the old one was actually reused, and then HDFS took care of syncing up everything and get me a second node offline. Now, of course, if I lose both nodes and all my storage, I'd have a pretty big problem. That's kind of what happens when you have a small cluster like this. But if you have a bigger cluster, a node dying kind of just becomes a routine incident. So this is what our deployment looks like currently. And now I'm actually going to be using that deployment to run a Spark task, because remember that this is just a Hadoop cluster, so we could use it to run just about anything. In my case, I'm going to use it to run a Spark task. So moving on.
I'm now logged into one of the client nodes of my Hadoop cluster, and I'll be using this to submit a task to the Hadoop cluster. So that task will be processing the Twitter feed to identify what people are talking about right now.
Basically the tags that are showing up in Twitter. So it's basically going to consume the Twitter feed in real time. So I just started it, and you can see my log output coming here. So right now the task is being scheduled on the Hadoop cluster. There it got accepted, so we're going to be waiting for the task to happen. So what happens now is that, let me actually log into that URL which is the tracking URL for this. And there we go. So this is Spark itself actually launches its own cluster manager on top of my Hadoop cluster, and this is the UI that you can see right now. So right now Spark is actually scheduling itself on top of our Hadoop cluster. You can see the tasks are starting to run. These are the tasks for the Spark job that we're running. And we can also see which nodes are actually active right now. And as you can observe, they're not all running on the same Hadoop node. I have one on the node number 3, one on node number 2. And of course, if one of those nodes were to crash, it would actually get replaced and rescheduled somewhere else. So you can see that processing is starting to run, and there you can see the top tweets that are starting to show up on Twitter. So if we wait for a few minutes, we can actually start seeing some trends that are starting to emerge. You can see that at this hour we have lots of Arabic speech, but we also have this that's called Bell Let's Talk. That's actually showing up a lot on Twitter today, and that's actually the beauty of real-time processing is that we can actually just Google it and figure out what this actually is, and you'll find out that today actually Bell is running a campaign where if you use that Twitter message Bell Let's Talk, they'll donate 5 cents to the research against mental illness. What we can tell right now, just by standing up this Hadoop cluster, is that this is actually pretty popular, since it's actually the thing that's being tweeted the most right now, as you can see according to our stats right here. So that kind of goes to show, just one note, of course, just a quick disclaimer, Bell is actually not a Scalr or as far as I know, a Nebula customer. This is just a very happy coincidence that they were running this campaign today during this webinar. So what this example goes to show is that using real-time processing, you can really get a you can very rapidly get a feel for what, in this case, social activity is. In this case, we can see that the top thing on Twitter today is this Bell Let's Talk campaign. If your company is running such a campaign that's public, you may want to be able to track its success. But more generally speaking, if you are if you're working at any customer-facing company, and today with social media, really who isn't? If you're running a customer-facing company, it's very useful to be aware of what people are actually saying about you. And this streaming example kind of goes to show that this is something you can do using Hadoop and Spark for real-time processing. So I'll just finish this up with a few notes of what's going on in our cluster, just to show you that this is actually something that's actually running. I'm not kidding. We have those multiple containers that are scheduled throughout our Yarn cluster. I don't have to do any work to schedule those. Yarn takes care of that for me. So it goes to demonstrate the separation of concerns that Yarn
provides for you. So now moving on, let's look at our data node and the
HDFS cluster. As you can see, my data usage grew up a bit since I launched that Spark job. That's because Spark is saving its backups to its data backups to the HDFS system. So in case it gets terminated or if a node crashes, it can pick up right where it left off. Back to Scalr, where we actually provisioned all of this. What I wanted to conclude with was to kind of show that beyond just actually provisioning that infrastructure, Scalr will also provide
for infrastructure reporting as well as monitoring.
So there we have basically two types of monitoring. One is actually knowing the load on your infrastructure. So that's typically useful if what you intend to do is one example of that is typically when you want to be auto-scaling. It's useful to look at historical data to get a feel for what exactly should your scaling parameters be. So in my case, I can actually go to my Yarn cluster and see exactly what the load averages have been. I was running my task a bit earlier. This is actually when I run a few tests, and when I run my tests, as you can see, the network usage grew up since I was pulling the Twitter fire hose, and the load averages went up too.
So now let's look at another form of reporting that Scalr is able to provide. So this is no longer about load averages, but this time it's about cost reporting. So this feature is called Cost Analytics, and it basically gives you a full picture of where exactly your money has been going. This is done using data
from Nebula, so knowing how many instance hours you consumed and so on and so forth. Scalr, by setting a custom pricing then in Scalr, you can start. You can basically start reporting on your costs, so identifying where exactly where exactly your money was spent. So in my case, you can see that my most expensive tier is the yarn tier, for example.
So now it's of course possible to drill down into the data and identify exactly like what servers were costing you the most money and so on and so forth. But what I'll do now is kind of summarize the what we've seen so far during this demo.
Using Nebula, you can really expose a pool of resources. So that cluster of Nebula kindly provided for this demo is backed by a lot of infrastructure, and as an end user of that cluster, I can kind of get a small piece of it, which I'm then able to consume through Scalr, where it's possible for me to kind of design my infrastructure, set up my Hadoop cluster, prepare it, design it, and then launch it. And finally, we saw how actually using extracting social feeds can be useful. So we currently have, as you can see, this is actually part of the. You could see that this actually hung for a minute. That's because one of my executors crashed. Let me actually spin up just a bit. Hopefully I'll be able to find it. Yeah, as you can see here, one of my executors actually crashed. There are a few stack traces in this. It actually goes to show the redundancy that I guess by running this on a Hadoop cluster. I lost a few seconds of feed, but I'm actually back online right now. It's a chance we actually got to see that in real time happen. Okay, so now that being said, I'll hand it back over to Hui for a conclusion. So before we get to that, I'll just want to invite you to feel free to ask questions if you'd like. You can submit your questions through the GoToWebinar UI, and we'll be happy to answer those questions as soon as Hui is done with the summary. So if you have any questions, now is a good time to ask them. Hui, back over to you.
To quickly summarize, the value that streaming analytics and continuous monitoring hinges on the ability to anticipate your needs, to recognize when your needs change, and to proactively adjust to those needs as they unfold. Big data technologies such as Hadoop Yarn and Apache Spark can build processing workflows to parse, categorize, and score information in real time, therefore enabling businesses to operate in real time to maintain that competitive edge. Data processing tiers, more particularly the infrastructure tier, must be able to auto-scale to accommodate the volume, variety, and velocity of big data. Nebula's turnkey private cloud and Scalr's intelligent cloud management platform meets these demands, where it can auto-scale the compute and storage resources on demand to process data feeds in real time as they grow. We thank you for your time today. For more information, please visit the Nebula website or Scalr's website, and we're going to walk through some of the Q&As at this time, and if you have additional questions, feel free to enter them in the chat window.